All right. Since we're already running late and it looks like a fairly full room at this point, I think I'll start. Hi, I'm Stefan Karpinski. Presumably you've heard of Julia if you're here. Otherwise, you're in the wrong room. I'm one of the co-creators of this language, together with Jeff Bezanson and Viral Shah. We started this project back in 2009, based on our own personal frustration with the existing tools in the numerical and technical computing space. So I think we're all what you could term, expert Matlab programmers and have a sort of love-hate relationship with Matlab. And our patron at MIT, Alan Edelman, who's the fourth name on this list, is actually the first. He was the first user of commercially licensed Matlab. So he has a very long and very mixed relationship with the language because he keeps trying to replace it. And Julia looks like it might actually be succeeding in that direction where his other efforts didn't quite pan out. Without further ado, I'll get going with my talk. So this is an interesting space. This is like a very different sort of comparison and language space than everything else that's going on at this conference. I think the things that we get compared to often is, R, MATLAB, Mathematica, SciPy. I mean, some other smaller names that you may or may not have heard of. But it's a very big, populated space. I mean, there's sort of like almost as many things in the like general programming language space as there are in this like niche area of just technical computing systems. So one of the obvious questions to ask is, what actually makes something a numerical or technical language? So the obvious answer is that it's just something that specializes in numerical work, right? That's the sort of obvious thing to say about that. And that sort of sheds a little light on why there are so many things in that picture. It's because everything specializes in a particular way. So for example, MATLAB, the idea of MATLAB initially was that it's just everything is a matrix of complex doubles. And that's actually a brilliant, brilliant type system until you have to do something else. Until you have to use something that isn't a complex, a matrix of complex doubles. And then all of a sudden you start having, trying to cram, make strings into some sort of array. Which is weird because you only have matrices. So they're actually not even one-dimensional arrays. They're actually two-dimensional arrays of characters. It gets very, very awkward very quickly. In R, there's sort of this very, complicated data type of a data frame, which is sort of one of your built-in fundamental types. And that's a little strange to have something so sophisticated. I mean, the only other language I can think of that has something so complicated built in as a basic data type is PHP, where their hashes are really this sort of crazy amalgam of many different data types in one. And another fundamental design principle here was the idea of representing the fact that you have missing data at a very basic level. So anything in R, a floating point number or an integer or a string can be NA, which means not available. It means we didn't have this data. And that's important and treated specially in various analyses in appropriate ways. But this complicates your system in a very deep way, right? Because you now can't just add two floating point numbers. Now you have to look at them and be like, well, was one of them NA? So the hack they use there is to use nan for that. But you can't use nan for integers, for example. So what they do instead is they use the minimum, the negative integer value, the one that doesn't have a positive, pair. Is the special NA value. But now that means that every integer operation has to be checked, right? You have to look at it and be like, oh, is it this special value? If so, do this thing. If not, do an actual regular operation. So you pay this cost of overhead, and it's very hard to optimize things as a result. Mathematica is interesting because it's not really a numerical language, it's a symbolic language. So it really takes the idea of symbolic computation to its logical conclusion. And I think it's because everybody has their own angle that they're approaching numbers and numerical computing from that you have this explosion of things on that previous slide. And why people come and make a new one, because they're like, well, that's not really the angle I was looking for. So the question is, what's Julia's numerical specialty? And the key answer here, which may be surprising, is that we don't have one. We don't make any of those sorts of decisions. We're not looking at a particular numerical angle. We sort of have stepped up a level and said, well, what do you need in a language so that you can define your own numeric types and their own behaviors in the language itself? And so instead of baking them in, we're going to give you all the tools you need to make your own. And you know, the question is, why is this hard? You know, why hasn't anyone else done this previously? I mean, people have tried, and Fortress is actually a really good example, and they came to a lot of the same decisions that we did. Not because, you know, they obviously didn't copy us. I don't think Guy Steele has ever heard of me. But, you know, the fact that we came to the same conclusions is for a reason. It's convergent design. So this is, you know, numbers seem really easy, right? They seem pretty basic, but they're actually really hard, surprisingly difficult. A huge, huge amount of the code and specification of pretty much every programming language ends up being devoted to numbers and arithmetic and their behavior. And just, you know, I'm not just talking about things like on that, you know, list of numerical languages. Those obviously, like, you know, they special case, and they're special for numbers. They're supposed to be numeric. So it makes sense that they have a huge amount of, you know, special case stuff for numbers. But, you know, even scheme in C. So I'll come back to the slide in a second, but I just want to take a look at this. This is the table of contents for the R6 RS spec. And it looks, you know, there's a lot of different material here. It's a very, like, notoriously simple and concise language with a relatively small spec. This whole chunk here is all numbers, and that whole chunk over there. This looks bigger, but that's just a, you know, visual artifact. That section there with arithmetic and booleans, the arithmetic, every other section of the base library is like at most 1 page, right? That one is 9 pages. It's you know, the giant among dwarves, and it's you know, much more complicated than you would necessarily anticipate it being. The same thing. It ends up being about 20% of the spec is dedicated to numbers and arithmetic. I was hoping for like 50 when I started looking at this, but you know, okay, 20 is still pretty big. And C is similar. It's about 20%. So the kinds of things you need to special case are, well, I mean, the obvious one is syntax, right? Numbers have, you want special infix syntax for things. You don't want to write necessarily plus of, you know, A comma B. You might want to write it that way sometimes, but you also want to be able to write A plus B. You want to be able to do exponentiation and various other things. If you've tried writing out a polynomial in S expression syntax, it's very difficult to read. It's certainly much harder than the mathematical notation that we're used to. But we also want special behavior. So in most languages, operators are not functions. You can't write plus as a function. So I mean, C is a good example, right? The plus operator can take, you know, functions can only take a fixed, you know, set of argument types in C. There's no polymorphism whatsoever. But plus can, you know, you can add an int and a float and a float and a float and a int and an int and all manner, and even C99, you can even throw a complex number in there. And that's why the spec gets so big, is because you have to bake in these rules for how those things promote and how they combine and how you convert between them. So this polymorphism is sort of baked into how mathy things work. You know, indexing in Mathematica is insanely polymorphic. Just doing basic things like addition is also. A couple other sort of interesting things that, you know, numbers are naturally immutable. There was a bug in an very early Fortran compiler that allowed you to mutate integers. So what this meant is that you could assign a different value to the number 2. And then anywhere you use 2, you would get that value. And I mean, obviously you're like that, no, you can't do that. You can't change the value of 2. 2 is immutable. 2 is 2. So I think numbers are really the prototypical immutable data type. So if you're going to want to define your own numeric types, you want to be able to express the fact that they're immutable. Otherwise, you're going to have, you're going to try to define complex numbers, and just semantically, it's going to be weird because if you don't use full copying semantics, and you wanted to use reference semantics like scheme or Python, then you're going to make an assignment, and then z equals something, w equals z, and then you change the imaginary component, and they both change. And you're like, but no, that's not what I wanted. So you want immutable types. You also need to be able to represent them compactly. Well, I'll get into sort of how we address a lot of these different things with the design choices in the language. There's a couple other things just to make things interesting that scientists and people who do numerical work want. They want extreme convenience. They do not want to mess around with making your type system satisfied. I mean, some people are okay with that, but a lot of mathematicians and physicists that I know would just not put up with it for 2 minutes. It's just not going to happen. They want code that looks like pseudocode. They want FFTs baked in and big ints and all this other stuff baked in that has to come sort of standard shipped with what the thing they download. And they want really, really good performance. So this is a bunch of interesting things to try to satisfy at the same time. Traditionally, the way we have gotten performance and this sort of high-level thing is to have two languages. Right, so you have your high-level language, and then anything that's performance critical you implement in C or Fortran. And that's actually a really reasonable compromise, and it's worked very well for a long time. There are a lot of benefits to be had from being able to write things in the high-level language as well. One of the ones I didn't anticipate being as powerful as it is the fact that because most of the language is written in itself, people get suckered into being developers. So they come as users. So a good example is like NumPy, right? Matlab's not a good example because you can't modify Matlab legally. But NumPy, you totally can. You're allowed to go in there and change it. And they welcome that, unlike R. R is actually very much it's very hard to submit to R for totally social reasons. But with NumPy, they welcome it. But when I was at SciPy in 2012, I expected, because there are so many people using SciPy, that they would have tons and tons of developers. And it turned out they don't. There's only 3 or 4 people who were qualified to actually hack on the internals. And that's because it's this crazy, crazy C code that's not just C code. You also have to know CPython, and you have to know how NumPy works. And you have to, it's just so much stuff you need to know. And we've had people contributing core pieces of infrastructure after programming Julia for 2 weeks. One guy, Carlo Baldassi, came and programmed Julia for about 2 weeks and then wrote a bits type array which is a packed Boolean array that just uses 1 bit per Boolean. And it's a complicated piece of work, and he's a very good programmer, but he didn't have to be steeped in many years worth of knowledge to be able to do that. So just a design overview of the language, and I know I made this too long because it does not fit on the screen all at once. Julia it's high level, it's dynamic. It's high level meaning that you can write A times B, and it could just be 2 integers being multiplied, but it also could be huge matrices that are being multiplied, or it can also be a distributed matrix that's living on a cluster of 1,000 machines, and you're multiplying it by another distributed matrix. So that's very high level at that point, if you just write A times B to make that much computation occur. It's dynamic. I think we all kind of know what that means. I'm going to talk about it a little bit more in a second. It has unusual for dynamic languages. It has an expressive language for talking about types. So I mean, all dynamic languages, if you say they're untyped, it's just not true. That everything has some type. You just don't have a way of expressing it. In some languages you do. Ruby, in particular, and Lisp, they have, first-class objects which represent the types that things have. But you still don't really have a good way of talking about it very much. You can't say that something is of a particular type. So we have a fairly sophisticated system for that. If you're really into type systems, it's parametric dependent. The parametric is invariant, not covariant or contravariant. Concrete types are final. That's actually turns out to be very important. If you have an implementation of something, you can't subtype it. It sounds restrictive. It actually turns out not to be a big deal. It's surprisingly, because you can make various abstractions and write code to them over that, you actually get pretty much all the things you wanted from inheritance anyway, because you can inherit behavior. The only thing you're missing is the ability to tack a couple of fields onto something, which is really usually not that useful anyway. One of the design goals was to make it unobtrusive, so if you want to write code that does not mention types at all, you're totally free to do so. And it'll run fast, and it is not a problem at all. The type system is only there for the cases where suddenly you need to express the fact that this array only holds floating point numbers, and therefore you can represent it compactly, and it has the same layout as LAPACK or FFTW or something expects. Multiple dispatch is top to bottom. So everything you interact with, in the normal course of programming, every function is generic. You can extend it. You can, for example, take, the built-in plus operator. It's my favorite operator. I keep talking about it. You can just add new methods to it, so it can operate on new types. You can, make new different combinations of things work. No problem. Everything's open. That's sort of the OO heritage. So the trick there, of course, is making it fast enough. We have sort of fancy things that multiple dispatch systems traditionally don't have. I'm not going to talk about it now because I'll talk about it in a second. We've quantified methods in diagonal dispatch. But metaprogramming, I actually don't really think metaprogramming is all as interesting as it's cracked up to be. I just think there's no excuse not to have a dynamic language be homoiconic. There's like no design cost. You can just do it, and it doesn't cost you anything on the flip side. It's a little bit of complexity in the language, but it's not complexity that comes at any expense. It's like there's no performance trade-off, for example. It's just like the way you really want to do code generation. Concurrency and parallelism, I kind of have to mention this because we're at a very distributed systems heavy conference here. Coroutine-based I/O and a distributed global address space, so you can have references to things on other machines and pass them around. I was during the keynote this morning, I was sort of thinking about how nice all of these immutability and concurrency approaches that Erlang and other similar languages have, and wishing we could have them, but we can't, because we have a very different reason for distributed computing, which is that we don't you have so much data that you can't fit it on your machines, so you need to split up the problem across 100 machines just so you can load your data into memory. And at that point, obviously, making copies of it or just appending to it is not an option. You can't do that. You actually have to mutate your data. Just for performance and overhead reasons, you can't, which is unfortunate. I really wish. I love the approaches that Erlang and Clojure take with that sort of thing, but it's not an option for us, I'm afraid. So just to get a little real here, I'm going to look at some code. So, oh man, suddenly we have a lot of performance tests. So these are this is our performance. Well, maybe I'll just look at the web page if you haven't looked at this. This is these are actual performance benchmarks that we time. And this is sort of the untyped, unobtrusive version, which looks a lot like Matlab, where you just, define a function. This computes 1 point in a Mandelbrot set. You give it z, which is some complex number. Presumably, it could actually be anything because we haven't typed it. So this will apply to anything. The expectation is that it's a complex number. And you just write, your little loops and return stuff and, take some squares and add stuff. This is more Matlab, even more Matlab. You wouldn't want to do this in Matlab. You could do it, but it would be really slow because Matlab is not very good at for loops and such things. This runs at C speed in Julia, so you don't have to mention types to get the good performance. This is just some matrix manipulation. You generate some random matrices, take some powers and traces and whatever, and this is also it's within 2x of what you would write by hand-coded C that does everything in sort of like an optimal way. But then there's also very different styles of coding Julia. We have these one-line function definitions that let you do cool, it's very common to write very small definitions, which is very uncommon in Matlab, for example, because they require you to make a file for every single function. So you sort of like cram everything into these huge sprawling functions. We have tons of very small definitions like this. Another example. So if you want to define your own type, so for example, complex numbers are just defined rather simply in the language. So here you see immutability in action. This declares an immutable type. It's a complex number, and then this declaration says that it takes a type parameter, t, which is some kind of real type. So there is actually a complex type for every real type you can lay your hands on, even new ones that you happen to define later. This thing is itself a type of number. It has two fields, re, which is of type t, and im, which is of type t. So those have to be the same real type. It's sort of usual programming stuff. And then we provide a couple of different ways to construct one of these guys. And I'll talk about this a little bit more later. This promotion system, this is just a function defined in Julia that takes two objects and figures out what a common type to promote them to is, and then converts them to that type. So a lot of very generic things can be done with this. This, allows you to do stuff like, well, this is two reals that I want to turn into complex, right? So if I have complex 1 and 2.5, I'm going to get a complex float, 64. Whereas if it was just 1 and 2, they're both integers, so now I have a complex integer. And that promotion system applies, so that definition actually applies to new things that haven't been defined yet. So if I define a new real type and I explain to the system through a couple of method definitions how to promote it and how to convert it, suddenly it'll just work. And that's very handy and extensible. And it's great for people who do numerical computing and do actually want to do things like define their own numeric types and have them be efficient, have them have the nice syntax that you're used to from everything else. All right, so why dynamic typing? We sometimes quip that Julia is dragging MATLAB programmers halfway to Haskell. So why not all the way to Haskell? And like I mentioned before, I don't think I could convince most mathematicians, despite the fact that they're mathematicians, and you would think that they would love the Haskell type system. I don't think I could convince most of them to actually put up with the type checking. There's also the issue that when you're working with data, you really, really want this exploratory, interactive, tangible property of it, right? When you're typing things into the REPL, I want to say that A equals random. I want to be able to just sort of do this and see what the result is immediately. I know it's the same thing in principle as writing a C program that does this, but it just feels real to me. It feels like I'm touching the data. And that's really, really essential to this kind of work. And that really sort of dictates a dynamic language. Scala does an amazing job of having a REPL and being sort of feeling dynamic despite being static, but I think that being actually dynamic makes this less of a problem. Dynamic languages also have this property that the customer is always right. The program will just say, okay, that seems like a bad idea, but I'm going to try it anyway, and we'll just see what happens. You can do things like have a function that sometimes returns an integer and sometimes returns a string. Okay, if you really feel like doing that. And it just kind of gets out of your way and lets you move on with your life. We are actually, I really like this quote. Leah Hansen was a hacker schooler, and while she was learning Julia, she observed this. She kind of had this epiphany moment where she clicked and she got it. And she was like, Julia uses the type system in all the ways that don't end up with me arguing with the compiler. So for performance, for documentation, for expressiveness, for dispatch, so being able to express complex polymorphic behaviors, but never in the way that says, you can't do that. No. And I'll always just say, yeah, fine, we'll do that, and we'll see how it goes. If you don't call this code, it won't be a problem. If you do call it and it's broken, then it'll be a problem. She's actually working for her master's thesis on what we're calling a type critiquer, just sort of like a type checker, but is a little gentler. It's a little more hands-off. It'll just look at your code and be like, this might not be the best idea. This is probably going to be a no method error. This is probably, you know, going to fail for whatever reason. Or a crucial one is that, for example, you know, a loop, the type of a variable changes over a loop. That's a terrible performance trap. And even if you do optimize, there are tricks we could do to optimize it. But it's actually a bad idea because usually it means that you also have type instability. So a good example of this is so let's say, okay, so t equals 0, for I equals 1 through n, t plus equals 1 over I. And then we just return t. Okay, so, you know, you do, okay, f of 10, f of 5, okay, that's good. This is actually a performance trap because the type of t changes over the course of the program. Initially it's an integer and then it immediately becomes a float. So we could actually fix that by peeling off one iteration of the loop, and then the main body of the loop would just be consistently float. But there is always this case where it returns an integer. So we're actually just hiding a deeper problem, which is this function returns different types. And so even though you're allowed to do that, you don't want to do that because it has terrible performance properties, and it sort of has implications that sprawl out through the system if you have poorly typed functions. And that's one of the things we've done with the languages, like be very careful that the entire standard library has good type behavior, even though it doesn't have to. Which is, you know, a design consideration that was not made when most dynamic languages were designed. So a little bit about multiple dispatch, the way it works. It's actually, this is basic multiple dispatch. If you've used any sort of, seen any sort of multiple dispatch languages, this will be completely normal. Writing a : any says that a is of type any, but everything is of type any, so that's actually equivalent of just leaving it off. So this is, you know, this is the same as that. It does nothing different. You can say, I want, when a is a number and b is a number, I want you to call this version of f. And it will return the string a and b are both numbers. You can do less specific things, like if a is a number but b is whatever, it's just type a as a number. Implicitly, even though there's no negation going on, because you always call the most specific version, if b is a number, this will not get called because the first thing will get called. And likewise, if, you know, a is a number for this fourth method, you know, if a was a number for the fourth method, it wouldn't get called because you'd call the first one. And then you can do more specific things, like if they're both integers, do something else. So, you know, the obvious thing here, you can just try it out. You're like, okay, those are both numbers. Okay, a is a number, b is a string, so we're calling the correct method. A and b are both integers, it's as expected. Neither of those things is a number or an integer, so it's just, you know, gives you the fallback. Crucially, this f is a single first-class object. You can pass it to other functions, like methods is just a regular function that just prints, you know, shows the methods of f. You can pass it around. You can assign it to another variable. You can do all the functional programming things with it. That's the functional side. The object-oriented side is that it's extensible. You can add new subtypes that it applies operations to, and I'll talk a little bit more about that in a second. Some fancy things, we've never added any feature that was fancy just for the sake of fanciness. We encountered this because we were trying to define numeric behaviors in the language, and we needed it. So this is what we call diagonal dispatch, and I think we just made up that name because I don't think any other language has this feature. So what this method definition says is it says f, where f is a method parameterized by a type parameter. So for all t, where t is some subtype of number, define this method f for, you know, where a is of type t and b is of type t. So the difference between this and the above definition where we just had I'm having scrolling issues, where we just had a and b both be constrained to numbers, is that these have to be the same kind of number. And that happens pervasively in mathematical stuff, where you're like, I know how to do this operation if they're the same type of thing. If they're not the same type of thing, I have to do something else. I probably have to promote them. And you know, your C compiler is doing the same thing. It has rules baked in to do it. It knows that in order to add an integer and a float, I need to convert the integer to a float and then do the addition. There's no add an int and a float instruction. That doesn't exist. So we can see this in action. I give it 2 big floats, and it recognizes that A and B are both big floats and calls this method instead of the more general number method. You can see that for big ints it also works, but in this case the integer rule is more specific. Because if you look at the sort of space of possible combinations of types, that is strictly more specific, so we call it. Doesn't apply to strings because we had that number constraint. It of course doesn't apply when you have only one argument. Yeah, okay. So, any questions about that? Oh, the reason it's called diagonal, I don't know if this makes sense to people, if it's clear why it's diagonal. It's if you have a table of the possible types of A and the possible types of B, the things that this actually will dispatch on are the things down the diagonal. So that's why it's called diagonal dispatch. Vararg's methods. Vararg's functions are, you know, they take in a variable number of arguments like printf in C. These are a compiler implementer's nightmare, but they're really, really nice. Everybody really likes interacting with them, so you have to have them pretty much for the sake of your programmer happiness. So this is a definition, two method definitions. I apologize for the wrap here. You never know what size screen you're going to be on. The first one says that I'm going to have 0 or more arguments that are all numbers, and then I'm going to do this thing. And inside the method body, you have access to args as some sort of, you know, iteratable collection of things. Often a tuple, but it can be other things too. The second method definition is subtly different again. It's one of these parameterized method definitions. It says f for any t that is a subtype of number, I want to have f with 0 or more arguments that are all of type t. So the difference here again is that it's like n-dimensional diagonal. It only applies if they're all of the same type. And so we're gonna, one of them is gonna print heterogeneous and the other one's gonna print homogeneous. I'll leave this one out for a second. So you can see, okay, if you only have one argument, obviously it's homogeneous. There's nothing to disagree. If you have 3 arguments and they're all ints, then you're good. It's trinary homogeneous call. If you throw a floating point number in there, now you have a heterogeneous call. There's no magic promotion ever happens. Promotion only happens if you ask for it. So in this case, it's just, these are different types of objects. This is an interesting case. The zero array has to be heterogeneous, and the reason is because there's no way to bind t to anything because you don't have any examples of it. And so you can actually use this t parameter as just a runtime value inside the method definition, and so we wouldn't have anything to bind it to, so that one can't apply. So technically, this one is actually 1 or more arguments because there's no way for it to be 0. Which is why you could, if you wanted to change that behavior, you could just, go like that and add it back in. Now you get, 0 array homogeneous call if you prefer that to be the case. Integers method is still more specific. Non-numbers don't do anything because we've always constrained it to be numbers. This multiple dispatch thing is actually really convenient, and I think one of the things I realized I was looking at Ruby, and I was like, there's a bunch of these things are actually doing multiple dispatch, except they just they baked it into the standard library and they did it with if-else blocks in C code. But they have all these different operations where, depending on the types of 2 of the different arguments, dynamically at runtime they pick a different implementation. So this is something that is convenient enough to put into your standard library. But there's no convenient way to do it yourself. You can, of course, write if-else blocks, but then it's not extensible and it's not particularly performant, and it's not very elegant. It ends up being monkey patching like you see all over Ruby on Rails. It's also very addictive. Once you start using multiple dispatch, you don't want to go back. You sort of are like, wait, what do you mean I can't just do a slightly different thing when this thing is an array or a hash or whatever? So what I realized is that it's actually very linguistic, that natural language has this multiple dispatch property. And you see, like, related meanings of the verb go depend on, what type of adverb you're pairing them with. This is a literal transition to, This is a literal transition to another location. This is like, the metaphorical go. It's a different sense. And you also have defaults, but they work with either of those things, right? So like you can have default, default values for certain things, and they can be before or after the verb, and this is very multiple dispatchy. So this is like how you would write this definition. I just thought that was kind of a cute example. I think it might explain why it comes so naturally when you start using it. So this is sort of the two sides of multiple dispatch. It's object-oriented on the one hand because it's all about subtyping, and you can add new subtypes of things, and you can have new behaviors and sort of stick them on there, which is exactly what you would do with a classical OO type hierarchy, and virtual methods, which you then provide specific implementations of. So I don't think it's very, it's not surprising that all these OO languages are emulating it, and it's a great way to express polymorphism, that type of polymorphism. There are other kinds of polymorphism, like generic programming. But it's also functional, right? Because this thing is a first-class object. In these object-oriented languages, there's no good way, there's no object that represents so let's say you have, a foo method in a lot of different related classes. There's no way to talk about that foo method in all of those classes as a thing itself. You can call them all separately. The closest you can get is a lambda that calls it, right? You can say, lambda of this thing applies foo to it. And so that gives you a function that calls that thing if you have lambdas. But it's not really the same thing as reifying that collection of operations as a single object. And that's what generic functions give you. And that's very powerful. And the combination of the two allows you to do things that either one by itself doesn't really let you do. So this is a fairly basic example of defining a new type. This is good not just for numeric stuff, but I'm going to stick with numeric stuff because it's kind of our wheelhouse and I really like this example. I'm going to define some modular integers. So essentially this is the meat of it. It's you define an immutable type because it's a number, so it's you want it to be immutable. Plus, you get really great. This definition ends up being no more overhead than just an int. It's the exact same size as an int. And you define the type mod int. It has one type parameter n, which is interesting. Is not a type. It's a dependent type system. So you can actually have a number here be your type parameter. So there's going to be a different type for every single modulus n. And it doesn't make, we're going to define operations between mod ints of the same n, but not if the n doesn't match, right? Because you can't add two, you can't add a mod 7 integer and a mod 9 integer. It just doesn't make any sense. It has one field, which is of type integer. We could make it, we could have a type parameter for the type of integer you want to have in there, but let's keep it simple as an example. And then a constructor, which is mod int. If you give it some k, I just want you to take k, reduce it mod n, and then just, the new pseudo function is just a way of constructing an object of the type that you're talking about inside of a type block. That's how we express the construction of a new thing. Defining some behavior is pretty straightforward. You just say, so let's, because plus is my favorite, let's do that one first. So we have plus is just a function, so you're just adding a method to it, and it has a type parameter n, and then you say a is of type mod int n, and b is of type mod int n. This type parameter here is now serving the role of enforcing the fact that a and b have to be of the same type. They can't be of different n's. If you have a modular integer of one n and a different n, this is not going to apply. You're going to get a no method error. All you got to do is just add their inner fields and then construct a new mod int out of it. All the other definitions are very similar. So let's just do a little code with that, see how that goes. I'm using it, so now I have a mod int type. You know what, this is, Sometimes this gets a little, I'm using this IPython/iJulia notebook thing, and sometimes it jumps around a lot, so. Okay. So that's a type. You can, construct that. That's a type. If you want to make one of these guys, you just, say that. Okay. Straightforward enough. I'm just going to make up some other random number. Okay. And so now already we can do A plus B. And that works. It just does what, A plus B plus B plus B is going to wrap around. So that's exactly what we wanted for modular behavior. If we, for example, try to do, so A plus B works because they're both mod 11. If we try to do A plus mod int 13 of some number, no promotion exists. So it's not quite the no method error, but it's, oh, you can't see that at all, but you can kind of see it. What ends up happening is if you look at this, what it does is it calls this very generic fallback function defined here for plus, which basically says if you got two numbers and you have no idea how to add them, promote them to a common type and then add them. The crazy thing, the hard thing to do actually is that if you look at, for example, the code for plus on an integer and a float 64, if this is not fast, you're kind of screwed. So the LLVM code for this is just signed integer to FP operation and then a floating point add, and that's it. So the tricky part is to somehow take this, all this abstract layers of definitions, which invokes promotion and splatting and all sorts of insanity, and somehow manages to figure out that this is all you actually need to do. And that's sort of the secret sauce. That's how we get good performance, despite having all of this abstraction. So interestingly, you already have a lot of stuff that's very powerful beyond just basic integers. So map mod int 11. I'm going to create a bunch of random. So that inner expression creates a random 5x5 matrix of integers between 1 and 1,000. And then I just I map the mod int 11 constructor over it to get a matrix. And you see I get an array of modular integers. I added a little secret sauce here. These two show expressions make modular integers print nicely and in arrays. But it's nice. It's like 2 lines. It's very simple. You already can do things like this. You can do, for example, a squared. Takes a second because you can see the JIT happening. Second time it's instantaneous. Because the first time it's never done this before. You can, this is a very efficient generic definition of matrix exponentiation. If you want to define another matrix B, which is, going to have slightly different values, this can also work. And of course, you have, A plus B. So all of this came for free from just defining plus and times. And of course, we also added minus. We also already, from these two definitions with the convert and the promote here. So what this is doing, convert is saying, if the first argument is the type object mod int n, and I have an integer and I want to convert it to that type, this is how you do it. You just apply the mod int n constructor to it. That's it. It's pretty straightforward. The promote rule is hooking into that promote system, which is all defined in Julia, and telling it that if you see a mod int n object type and the int type, the thing that wins is mod int n. And this is how all of the promotions, like the float and int stuff, is done. And that's all you need to do. And now you already have, a plus 1 will work, even though 1 is not, 2 times a will work, 2 times a squared will work. All of this stuff just works. You also, for example, you can get, 2a cubed minus, 5b squared plus 1, all of these things just happen. Actually, I shouldn't do the negative thing because that kind of exposes the fact that the modulus operator is doesn't do the right thing. This is one of my pet peeves about x86. I'm like, we've got a million instructions at this point, and you can't give me a proper mathematical mod. So the mod instruction is actually, has less good code gen than the remainder instruction. So just throw me one instruction, man, come on. So anyway, I hope that sort of displays a little bit of the stuff you can do. We've sort of been addressing the expression problem here without realizing it. I don't know if anybody's familiar with this, but my favorite definition of the expression problem is Mats Torgensen's, because he doesn't really throw in type checking or modularity as red herrings. I don't think those are essential. Really, it's about, to what extent you can have new types that you apply existing operations to and new operations that you can apply to existing types. You need to do both of those things. And the former is relatively easy in OO and hard in functional, and the latter is easy in functional and hard in OO languages. And we just did both. Or actually, we didn't create a new operation, but we can do it right now. We're going to create this foo operation, which is defined to do this expression with modular integers. It infers the type of n from the modulus of the objects, but in the case of integers, two integers, we're going to define it to just use mod 11 because that's apparently my favorite modulus. And what you can see, what's interesting is that the code for this ends up being very straightforward. This goes from 2 ints to a single int, and all it's doing is basically these end up being no ops, and you just end up doing some remainder and shift left and addition operations. Which brings us to performance. So how's the performance of this whole business? Seems very complicated. Seems slightly implausible that any of this would be fast. So this is a little hard to see because of the colors and because of the screen, but basically this is a log scale plot of performance across a couple of different benchmarks. They're micro benchmarks. We originally wrote them because we were bad at them and we wanted to get better. But now they're real world code is also comparably fast. We have a whole suite of test cases where we're not as good as we would like to be, but in general, we're within 1 to 2x of C. So this is all relative to C performance. This is the amount of time it takes in each of these different systems to execute these various micro benchmarks. And you can see that Fortran is very fast, except for string parsing, which it does very poorly at. And it's insanely fast at recursion, apparently. And various other languages. Go is pretty fast, but has a little bit of a spread. Sometimes you get up to 10 times slower than C. Octave is just a dog. It's so slow. Like running the benchmarks is all Octave. I'm just waiting for Octave the entire time. And Python is a fairly fast interpreted language. Mathematics is impressive. JavaScript is crazy fast for something so dynamic. Interestingly, so there are a bunch of very fast dynamic languages these days. So JavaScript, V8 was the pioneer there, but now there's a bunch of very fast execution engines. Luigit, Mike Paul is a total genius at writing fast dynamic languages. PyPy is a really impressive project. It gets pretty good performance. We do not work at all the way those do. Doing totally, totally different things. And I think a good way to put it is Carl Boltz, who actually works on PyPy, at dinner a couple weeks ago, he said, I didn't get it at first, but he was like, Julia just does static compilation at runtime. I'm like, what are you talking about? We're dynamic. And it's because when I think of JIT, I just think like you defer your code generation until when you actually need the code. But what he's talking about, what other people seem to have thrown in with the JIT definition is that not only are you doing that, but you're also doing tracing to try to figure out types and guess them. You're also doing speculative code stuff where you at the extreme sometimes will generate code that doesn't do null checks but then waits for an exception to occur and then fixes the problem afterwards. Right? Crazy, clever things like that can get you good performance even when you can't infer the types of things. What we've done instead is we've just leveraged the language design to try to make it easier to do those things so we don't actually have to do any of that stuff. I mean, some of the things are really, pretty basic decisions, but they're important for performance, like use native data types. If you have integers that never overflow, then how are you going to make that fast? It's really difficult. Matlab uses saturating integer arithmetic, which is good for signal processing and terrible for everything else. It makes integer addition and multiplication non-associative, and they don't distribute over each other, so you like cannot optimize anything. The immutable types are really important. The fact that concrete types are all final, you can't inherit from them, that allows you to you know, once you've narrowed it down to int, there's no subtyping int, so you're done. You're good. You know that this thing is going to be an int. You also know that ints can't get bigger. It's not like anybody can come along and make a subtype of int that is, you know, twice as big or 10 times as big. So that means you can store them compactly in an array. Also, you know, in a format that C and Fortran are familiar with, and so you can call C and Fortran libraries without copying any data. I mentioned type stability. Obviously, we've been using type annotations, so you know, we're letting the programmer express things about the types of stuff. We don't have to just guess. We can actually let the programmer tell us when it's convenient to do so. Multiple dispatch. Not only is it crazy expressive and intuitive and powerful, but it also provides like amazing type data. Like you get all sorts of insane information that you know, the compiler is so happy about. And the way we leverage that is through this Dataflow type inference technique. And so just, it's not Hindley-Milner, it's not unification. In particular, unification is all about actually figuring out the exact type of everything. And so instead, what we're trying to do is put a conservative upper bound on it. So some of the time we can figure out the exact type. About 60% of expressions, and this is like totally ballpark hand wavy because it all depends on what program you're running. But in some somewhat typical code, in some sense of typical, we got about 60%. And the key thing is that performance critical code tends to be pretty well typed. You know, at the top of your program, you're doing some stuff with dictionaries of any to any, and you have like no idea what the types of anything are. But you know, it's your business logic at the top. But then you get down into some sort of like inner loop, and you know that everything is floating point. Tends to be the way that goes down. And it's really nice to be able to not care about types at the high level where you don't care about performance, and then in the same language also get really good typing in the inner loops. Interestingly, different than other systems, like the code with type annotations isn't static. It's still dynamic, it's just dynamic with better type information. And in particular, one of the things we can do is we can recover from transient ill-typed problems. So a good example, I'm not sure what order to explain this. Yeah, I'll just look at this code. It's pseudocode for what we're doing in the type inference engine. So on the one hand, you have, for example, you've inferred some stuff from looking at the code, and you know that two objects have to be of the same type. You don't know what the type is, but you know they're of the same type. So you have this type TT. You type intersect that because you apply a function to it, and you know that there's only certain methods to that function. So for example, let's say you only have this method to that function. What ends up happening is like now, neither of these are particularly well typed, but the intersection of them, which is what are the only things you know can ever happen, is actually completely perfectly typed. So that happens more, it's actually fortuitous that this works this way. It's really great. A more complicated example is you can have an abstract array. You know the element type is float 64, you don't know how many dimensions there are, and you know you're going to get a tuple with that many elements in it, but you don't know what n is. And then you apply it to a function that only works on matrices. Well, you know, and it only works on matrices, and these dimensions have to be integers, right? Because you know dimensions often are given as integers. So now immediately you actually know exactly what code to generate. The only thing you need to do is you need to put some type checks ahead of this maybe to be like, well, okay, if these assumptions aren't true, it's not that we need to bail out and execute slower code. We just need to bail out because it's an error, which is much easier to do. So a good example of this is this ill-behaved square root function. So our square root is type stable in that if you give it a floating point number, it always gives you a floating point number back. If you give it a negative floating point number, it just gives you nan. Some people don't like this, and they want it to give me a real number when the argument is positive and a complex number when the argument is negative. For performance reasons and type stability, that's a terrible idea. It also is often not what you want in code. If you write code that operates on reals, you do not expect a complex number to suddenly crop up most of the time. You actually want that to be an error. But you can define your funky square root that does this, and you can see that square root of 2 is a floating point number, square root of negative 2 is a complex float 64. So this is now this is poorly typed, and you can't really do great things with that in terms of code generation. But now we define a function that uses this x square root and says, y is equal to x square root of some square that I'm trying to find the square root of. And then I want to apply the hypot function to that, which, this is a totally nonsensical function. But it's just for didactic purposes. What we can do here is we define that, and we look at if, the system looks at the methods of the hypot function and notices that all of them are real. There are no non-real arguments. And so as a result, if you look at the code, this is this horrible sort of typed intermediate representation that we still expose to you, but it's like very hard to read. And you can see that at the end, the return type, we have inferred that the type has to be float 64. So what happened here is for a while we had bad typing, and then we recovered it. And the rest of the code that calls the code that calls x square root is has to deal with poor type information. The code that calls d doesn't. You have to have some runtime type checks in there, but you don't actually have to. The code that calls this d function doesn't have to worry about it. Some other things that I'll mention that we have, like I said, metaprogramming, Julia's homoiconic. I could give examples, but I'm out of time. Distributed programming. So you can hold references to in-progress computations that can either be in the same process or on a different process on the same machine or on a different process on a completely different machine. And you're connected via TCP, SSH, MPI, whatever. Nice things that, so, this is not always the easiest programming model. It's not as nice as, doing something like Erlang, but again, like I said earlier, we need to deal with the fact that people need to mutate huge amounts of data. This is significantly easier for a bunch of reasons than doing, for example, like raw MPI programming. This is sort of what the HPC world has converged on as like a good model for doing this kind of stuff. And some niceties that we bring to it is that any Julia-defined data structure just gets automatically serialized and deserialized. You don't have to do anything to make that happen. Clojures get serialized too, so you can write code. In particular, you can write a macro that then implicitly wraps something in a thunk and then sends the thunk across the network, and then you call it on the other side. And you basically just say at spawn and then something, and it just goes and does it. Remote references, so a reference to the operation that is in progress, you can also send those across the network. So you can delegate the responsibility for waiting for something to someone else. So this allows a lot of like fairly sophisticated, HPC-style distributed computations to be done with relatively little pain.
How do you interface with other languages?
We just call we can call C code very easily. So it's just it ends up boiling down to just a C call, like a call function, and same thing with Fortran. And then basically anything that exposes a good C API, which unfortunately does not include C++. So calling C++ is a nightmare, and it always is, right? C++ is only easy to call from C++. And even then, it's not even possible to call C++ from a different C++ compiler. You have to have the same compiler. C, no problem. Different compilers, there's an API. We can do it. We had libjulia. There's a C API, which it only just now is getting documented and standardized and totally rounded out. So that's not super mature. We're very good at calling C. We will probably in a month be very easy to call from C. It's already possible, but it's not as mature as it should be yet. We're practicing extreme open source. We've been on GitHub from day one because I foisted Git on everybody, which they weren't sure about at the time, but have subsequently recognized as a good choice. We also have a Git-based package manager, which I designed, and people thought I was a little bit crazy at first, but I think it might be coming around. I don't know. We'll see. It actually works now, which is really that's the real selling point, is that it actually installs things correctly, which was not true for the first 6 months of its existence a lot of the time. One of the design goals here is that if you have a package installed, you already have its source code, you already are in a position to make new commits to it, and you are already in a position to submit those. I'm going to live on the edge here and demo this. So for example, I'm going to k-nearest neighbors package. See how this works. Nothing to be done. Okay, I already have it. Okay. All right. So I am going to clobber the README. Okay. So, whoops, where am I? There we go. Okay. So, I'm going to go in there. We can see the git status is this. I'm going to make a git commit. Okay. How many screens do I have? Okay. So now what I'm going to do is I am going to submit that change. So this made a fork of the repository and submitted the change as a pull request. It hasn't actually submitted the pull request. The whole design here is that it pops up a screen at which you can review the clobbering you just did and then decide if it's okay and hit send pull request, which I'm not going to do because that's obviously not a good change. Okay, so that's it. That's what I got. I guess, do we have a moment for questions or?
Maybe one or two.
Okay. Yes.
I noticed where you talked about the solution for the expression problem.
Mm-hmm.
Your solution actually looks a lot like Go. Was that something that you actually looked at, or is it just like a happy coincidence?
Yes. Okay. So the question was that it looks like Go. Was that a coincidence? I don't really think it looks like Go, but I don't know. I'm actually not super. I'm somewhat familiar with Go, but I haven't done any Go programming, so I don't know. I don't actually think that's true. I don't think you can solve the expression problem easily in Go. But maybe you can. I don't know. The interfaces maybe allow you to do it.
So in Go, you can actually you can define the interfaces, and then your type automatically implements those interfaces if it matches the shape that you define in the interface. And you can then define when you define a type, you can then define the operations outside of the body of that type. So very similar to how you define your new numeric type in Julia, and then define the operations that you can perform on those types.
Okay, so the immediate answer is no. Clearly, if I didn't know about this, I wasn't influenced by it. But I really want, let's talk later because I want to see how Go does this and actually understand that. So,
okay.
Yeah. One more.
From theoretically, we can see that it's contain everything. Mainly, for example, metaprogramming.
Yes.
And it is done by itself, the same program. But I don't know how much the practical side, how much, who used it and how much it succeeded in that field. And the other thing about the community.
So I've been, I think the question was heard on the tape probably because she's got the mic. But I've been downright surprised by the eagerness that people in the numerical and technical computing field have adopted this. And I think they have the same frustrations that we did when we created this, which is that Matlab is really great for some things and then really awful for other things. And R is same story. And Python is NumPy is good, but it's like an awkward fit. The language isn't super really designed for these things, and so a lot of things become kind of difficult and hard to express and hard to do. And so we just wanted to do something that was better, and very much from a practical standpoint. I mean, I was a data scientist for a long time, and I was doing this stuff on a day-to-day basis. So this is the tool I wanted.
I haven't doubted that. You do excellent job. and it is really worth to study it and learn it, because it can, instead of learning many languages, it's one language which address all of these things. Yeah. But that means that it's as any language, begin and developed. Yeah. Developed by community. Yeah. And how much you have this community and how much explain that to kind of market this language for developer. Well, because there is need for such kind of language.
Yeah, the community, I love our community. It's very active, and there's some sort of pulse thing on here, right? There we go. I mean, you can see this in the last week. There have been, it's not a huge amount, but, it's like a bunch of pull requests, a bunch of other things. There's a lot of activity going on GitHub and a huge amount of traffic on our mailing lists. And we have about 25 people who have commit access to the main repo. So that's, people who have done a lot of work on it and are trusted to do things without, having to make a pull request necessarily. So I think that's a fair number of contributors for an open source package.
I think you did excellent job, really.
Cool, thank you. Thank you.